In this video, we will use a model of a Subway restaurant to talk about SMORE responses and SMORE plots. So, in a related video, we have talked about the model development and the basic verification of the model of our subway system. So if you have watched that video, you're probably familiar with the system and you know how to develop the initial model. But in this video, we're going to skip these two steps and we will start with the model that we have verified in that related video. So specifically, we're going to learn how to define experiment responses and how to interpret the risk and error associated with our simulation outputs using the SMORE plots or SMORE plots. Moreover, we will modify the initial model to compare alternative operating policies using SMORE plots. So the system that we're considering in this video is similar to a serial production line. So customers enter the restaurant and then they go to the first stage where they choose the type of bread and meat and cheese that they want on their sandwich. And then the customers go to the next stage, which is the oven. So if they want their sandwich toasted, the worker puts the sandwich in the oven and the oven heats the sandwich and toasts it. And then the customers will go to the third stage, which is the veggies station, where they put lettuce, tomatoes, and other types of vegetables and condiments on their sandwich. Once the sandwich is ready, the customers pay at the cash register, and after the payment is complete, the cashier puts the sandwich in a bag, and the customers then go to the drink machine and get their drink, and then they leave the system. The data that we're given are as follows. So the arrival rate is 32 customers per hour. The service times are all triangularly distributed for all of our 5 stages in our system. And the parameters of our triangular distributions are as follows. So for example, for the bread and meat station, the minimum is 1 minute, the maximum is 2 minutes, and the most likely value is 1.5 minutes. Similarly, for the oven, the minimum mode and maximum values are half a minute, 1 minute, and 1.5 minutes. The other thing is that not all of our customers want their sandwich toasted. So the data that we're given indicates that only 70% of the customers want their sandwich toasted and 30% get cold sandwiches. However, the current operating policy of this restaurant requires that we maintain first in, first out throughout the system. In other words, we do not allow customers who want cold sandwiches past the customers that are waiting for their sandwich to be toasted. As for the performance measures that we're interested in, particularly we want to evaluate server utilizations and also average time in system and expected number in system at steady state. So here is the model that we have developed and verified in the related video. And as you can see, we have our arrival process and inter-arrival times that are exponentially distributed with a mean of 1/32 hours. We have our triangularly distributed processing times for our bread, meat, station, veggies, cashier, and drink. And also, in order to account for the current policy that does not allow cold customers to pass customers that want their sandwich toasted, we have an empirical distribution. Let me expand this some more so you can see the distribution here. So we, for the processing time on the oven, we use an empirical distribution or a discrete distribution that randomly picks a value or processing time of 0 for 30% of the customers to account for the cold sandwiches, while the remaining 70% of the processing times will be triangularly distributed with the given parameter. So in this video, we're going to start with this model, and we're going to do more experimentation and analysis. So what I'd like to do is run an experiment, but this time instead of running the experiment and looking at the pivot grid, I would like to use something we call SMORE responses or experiment responses. So what I can do is go ahead and define experiment responses in my experiment table, and what the responses do for me is that I can display my output statistics in my experiment table without having to go to the pivot grid to see the values. So I'm going to define some of the responses that I care about. So the first one is time and system. I'm going to call it TIS, and in order to put the expression for the time and system, I can use the expression builder. So I know the time and system is related to my customer entity, so I can hit the period, and then I can go to population, and what I want is time and system, and I want the average time and system for my customer entity. So as you can see, the expression is customer.population.time-and-system.average. The next response that I would like to add is number in system. I'm going to call it NIS, and the expression for the number in system is again going to be customer.population number in system, and again I'm interested in the average value here. So before I continue, I would like to talk about the expression that we have for our response here. So remember, in our model we used an instance of the model entity definition, and we called it customer. And in SMORE, whenever we are interested in information related to a dynamic object in the model, we begin our function or expression with the name of the object instance instead of the object definition. That's why we start our function with customer instead of model entity. And the population basically tells us that we are interested to know about all of the realizations of this model entity instance that were created during the run. So that's what the second component tells us, and specifically for this response we're interested in the number in system for all of the realizations of the customer instance. And for the number in system, we would like to know the average number in system over all of the customers that were created. Similarly, for the time in system, again, we are interested in information about our customers, and what we're after is the average time in system for our population. So, like I said, for any dynamic object, we need to start our expression with the name of the object instance. So, as we will see shortly, for the servers also, we start our expression with the name of the server, and this is what I'm going to do next. But before I do this, I would like to mention that there is another video module where we talk about common SMORE expressions, and if you would like to know more about SMORE functions, I would like to refer you to that video module. The next response that I'm going to define is the utilization of my bread station. So I'm going to call it bread util. And for my station, I'm going to look for the name of this station. So I'm going to look for bread meat. And then in the list that is given to me by SMORE, I need to go to capacity, hit the period, and what I'm looking for is the scheduled utilization. So again, the name of the server .capacity, that's scheduled utilization, and I can go ahead and basically do the same thing for the other servers. So for example, for my second server, which is the oven, I can simply go ahead and type in oven.capacity.scheduled utilization. So another thing that we can do with responses is that we can define their units. So for example, for the time in system that I have selected here, we know the unit is time, and we can set the display unit. We can pick hours, seconds, days, weeks, whichever you want. We can also set objectives for our response values. So for example, you may want to minimize time in system for your customers in the system, and we can also specify lower and upper bounds for our response parameters. Now, the objective, lower bound, and the upper bound properties are used in SMORE add-ins, such as the subset selection or some of the optimization packages that come with SMORE. But for now, we don't have any objective or lower or upper bound for our variables. We just set the unit time type for time in system, and for number in system and utilizations, we don't have any units. So I'm going to go ahead and define 3 more responses for my other 3 servers. So now that I have my responses defined, I can go ahead and increase my run length to 300 hours and add my warm-up period, since I'm interested in steady state analysis, and I can run my experiment. So I'm doing 10 replications, and as you can see, when my experiment is running, I can see the value of my responses in my experiment table. Now, these are the exact same values that you can extract from the pivot grid, but instead, when you define responses, you can display these values in your experiment table. But perhaps the most important functionality of experiment responses is that they will provide access to SMORE plots. So as you can see now, when we go to response results, we can see the SMORE plot for our different responses. So we can see the SMORE plot for time in system, number in system, bread utilization, and so on. So let me go back to my PowerPoint and talk about SMORE plots very briefly. So here you can see the different components of SMORE plots. So we can see that it not only gives us information about the sample mean, but it also gives us information about the maximum of our sample and the minimum of our sample. And also you can see that it gives us information about the lower percentile value and upper percentile value, the median, and also it gives us information about the confidence interval over our lower percentile, the confidence interval over our mean value, and the confidence interval over our upper percentile value. SMORE plot, or basically SMORE plot, is based on a paper by Barry Nelson, the MORE plot displaying measures of risk and error for simulation output. And I would like to spend a few minutes to talk about what we mean by measures of risk and error. So going back to our experiment results, here is the SMORE plot that we have based on 10 replications for our time and system. So I can click on the histogram and observations and rotate my SMORE plot, so you can see the individual observations, the 10 observations that we had of average time and system from our 10 replications, and you can also see the histogram of our observations, which is not very informative. So as you can see, I have a very wide confidence intervals on my mean and lower percentile, and I wasn't able to calculate any confidence interval on my upper percentile. So since we are basically in each replication sampling one observation of our random variable, which is our time and system, we can simply improve our or the accuracy of our estimates with running more replications. So I can go ahead and change my number of reps to 25. So now I pick up from the 10th replication, so I'm doing 15 additional replications. Now when I go to my SMORE plot, you will see that now I'm able to calculate confidence interval on my upper percentile, and my confidence intervals are shrinking a little bit. So let me actually remove the observations in the histogram and increase my number of replications to 50. So now I'm doing 25 more replications, and as my model runs, you can see that my confidence intervals start to shrink a little bit. And this shows that we have full control over our sampling error. So basically we can reduce our sampling error, which are indicated by the confidence intervals or the width of the confidence intervals in our SMORE plot, by basically running more replications, or in other words, sampling more observations. So let me actually go ahead and increase my replication number to 100, and now when I run my experiment, you will see that my confidence intervals will even shrink more, since I'm reducing my sampling error. The SMORE plot also gives us some information about the risk associated with our estimate, indicated by the percentile values, the lower and upper percentile values. So I would like to talk about that in the context of an example that I have developed here. So I would like to go to this Excel file that I have, in which we have two samples of size 250. So sample 1 and sample 2 both have 250 observations of a random variable in them. And when we actually look at the average values for the two samples, we'll see that the mean for the two samples are pretty much the same, very close to one another. But when we look at the 25th and 75th percentiles, we'll see that they're very different. So if we assume that these two samples are observations from two investment options that we have, you can see that the second investment option has more risk associated with it. In other words, in 25% of the times, it is possible that we make less than $112.25 dollars, or whatever the units are. And also, it's possible to make more than 137 with a chance of 25%. But in the other sample, in the first investment option, we'll see that the variability is much less. So that's basically what we mean by saying that the percentile values give us some information about the risk. So now what I'd like to do is go back to my model and save it as a different model. This time I'm going to call it passing policy. And in this model, what I'm going to do is to allow customers that want cold sandwiches to pass the customers that are waiting for their sandwich to be toasted in the oven. So in order to make this modification, basically I need to do two things. So since I don't send these cold customers to the oven anymore, I need to update my processing time for my oven. So it will just be the processing time for my hot customers. And the next thing I need to do is add a connector that goes directly from the output node of the bread station to the input node of the veggies station. So now when I hit run, what happens is Simio sends 50% of the customers. Let me speed up a little bit here. So it sends 50% of the customers to the oven after the first station, and 50% to the veggies. So what I'd like to have is to have 70% here and 30% here. So what I need to do is to click on my connector and then use the selection weight property to implement my logic. So I'm going to change this to 70, and I'm going to click on the other connector and select its selection weight to 30%. Now Simio sends 70% of the customers to the oven, and 30% go directly to veggies by passing the customers that are waiting in the second stage. So now we have implemented the alternative policy of allowing customers to pass those that are waiting in the oven. So here I have opened two instances of the Simio software package, and I have performed the exact same experiment with both models, basically the current policy on the left and the alternative policy, which is the passing policy on the right hand side. So I can either go ahead and compare my average values of my responses in my experiment table, and I can also go to my response results, to my SMORE plots, and compare different statistics of my responses. So for example, I have time and system selected for both policies here, and I can go ahead and compare the mean for the two policies. So for the first one, the current policy, it's 9.56. The average time in system for the alternative policy is 9.52, both in minutes. I can also compare the percentiles. So for example, the upper percentile for the current policy is 9.78, and the upper percentile of time and system for the alternative policy is 9.72. And similarly, I can compare other statistics such as the minimum and maximum, lower percentiles, and median of the two policies using the SMORE plots. Now remember that here we had to open two instances of the Simio software package to compare the two policies side by side. And in the future, we will learn how to use Simio referenced properties so that we can make comparisons all in one place using a single experiment.